Next thing we're looking at is scatter diagrams, which is something that you have seen before. We need to know the difference between a response and explanatory variable. So the response is the variable whose value can be explained by the value of the explanatory variable. In other words, explanatory is like your x, response is your y. So x is the thing you control, and then y would be the outcome at that particular level. Scatter diagram is basically when we just plot all of those points. So every ordered pair showing all the relationships between the two. We can do these by hand or on the calculator. We're really just going to mostly do it on the calculator just because sake of time, most of the stuff we're doing with it, we'll use the calculator for it. So this data is based on a study for drilling rock. Researchers want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So x is the depth where we begin, y is the time to drill 5 feet. I want a scatter diagram, and we're going to use our calculator to do that. So you need to go into your list. Your first column, the x will go in L1, the y would go in L2. Everybody get your data entered? So then we can go into our stat plot. Plot 1. I want to turn it on, and I want a scatter plot. So that's the first option. It just looks like little dots. And you notice it'll automatically say the x's are L1 and the y's are L2, which is what we want. I'm going to go to zoom and do number 9, zoom stat, and it'll take me to where my data is. So we should get something that looks like that. So we can use this to study our data. A lot of times I'm going to be asking you questions about this, like is it linear, is it a positive relationship, a negative relationship, is it a strong one or a weak one? So those are the things that we need to look at here. Linear basically means forms a line, so this would be a positive linear relationship. With an increasing line. This would be your negative linear relationship. And we could have things that are not linear. We're not really going to try to write equations for anything non-linear. So in algebra, we probably would have tried to make an equation for a quadratic or something like that. But for our purposes, we're really only concerned with if it's linear or not. So if you see some pattern, but it's not a line, we're just going to say non-linear. If you have points just kind of spread out all over the place, we can say there really is no relationship. So what do you think about ours? Did we have a relationship? Kind of. It's not amazing. They're kind of spread out, but we can kind of see a positive trend, so maybe a positive linear relationship just doesn't appear to be a super great one at this point. Okay. So to decide how good the relationship is, we need something more than us just saying, those look close together or those don't. We need a better, more scientific method of kind of describing that. So we're going to look at what's called a linear correlation coefficient. And this is just a measure of the strength of the linear relationship. Okay, so this R value could be positive or negative, indicating a positive linear relationship or a negative linear relationship. Basically, the closer it is to 1, the better the relationship is. Now, the formula is really ugly looking, but we know what a lot of these things mean. What's x sub I? Yeah, each x value. So each of the first numbers we put in a 1. What's x r? The mean of the x's. If we went into if we went to calculate the two variable statistics, we could get our x bar right there. What's the s sub x? Standard deviation for x. Okay? Y sub I would be each y in L2. Y bar would be the mean of the y's. S sub y would be the standard deviation of the y's. Okay, so we could find each of those things. What are we doing with them? Multiplying. So basically I would find each of those numbers and multiply them together. And then what's this symbol out in the front? Sum. So kind of like standard deviation, we went through, we subtracted from everything. So we would do this for each of those x's and each of those y's. Multiply those together and then add that whole column. And then what am I dividing by? N minus 1. N being the number of ordered pairs that we have. So it's kind of a tedious calculation. So probably like standard deviation, it would be something that you might do by hand once or twice. Most of the time we're going to rely on our calculator for it because there are a lot of numbers involved. It is on your formula sheet, so you do have that formula there. All right, so things about the correlation coefficient. It has to be a number between -1 and +1. The closer it is to 1 or -1, the stronger the relationship. So a +1 is a perfect increasing line. A -1 is a perfect decreasing line. If it's close to 0, then that means there's really no relationship whatsoever. There's no linear relationship. It is unitless, so we don't have to worry about any units. And it's not resistant. We've talked about resistant before. What does that mean?
It changes easily with an outlier.
Right, remember we said like the mean is not resistant because one outlier really changes the mean. Same thing with this. One outlier would have a huge impact on that linear relationship. So this is just kind of a visual. This would be when R is 1. I could draw a line, perfect line, that meets all those points. That's when R is 1. Here we see it's still positive. They're a little more spread out. So it's still close to 1. Here, this is more like what we had. There's a little bit of a relationship, but my R has gotten pretty small there. That's like a 0.4. And we could have the same thing with the negatives. These two cases, there's really no linear pattern. This one does look like a parabola, but R only tests if it's linear. So even if it makes a different pattern, you're going to get an R very close to 0 because it's not a linear relationship. So let's try one by hand, and then we'll do one on the calculator. Okay, I'm going to give us a small point to do by hand. Actually, let's do example 3 first because we already have this stuff in there in our calculator. We don't want to backtrack. Just like everything else, you guys have your books today, so I can show you. If you forget how to do something in your calculator, there are boxes that always show you what we're doing. So if you look, I don't remember what page it was on in this. Page 189 at the bottom of the book. It has the technology step-by-step, this blue box that kind of walks you through the steps. So entering the scatter diagram is not too difficult. Correlation coefficient. There is sometimes if your memory gets reset, it may not show up for you automatically. So anytime you don't have it, we are going to have to go through a step first. So we need to go into the catalog. So we're going to hit second and the 0 button on our calculator. And we are going to have to go down for a while. I need diagnostic on. Okay. So everybody should be doing this on your calculator because it is not automatically there. Now once we've turned it on, it will stay on unless somebody turns it off or the memory gets reset. But the default, anytime memory is reset, it'll turn off. So we're going to go to catalog diagnostic on and hit enter. We'll just say diagnostic on, hit enter again, it will say done. Okay, so anytime you're not getting your R, you have to go through that, and again, page 189 does tell you how to do that. Alright, so now we actually want to get our equation. Right, so let's go into, okay, we're going to go into stat, calculate, and we want number 4 of linear regression. Okay, our x is in L1, our y is in L2, so we enter through all of that, and I get this information. Okay, it tells us, so that was stat, calculate, linear regression number 4. So it tells me this is y equals ax plus b. My a, b, point 0, 1, 1, 6x plus 5.52, 7, 3. That's the equation for the line of best fit. And that will always show up if your diagnostics are turned off. You won't have that R squared and R underneath. The linear correlation coefficient, that is R. So my correlation coefficient on this problem is what? Okay, so we just used, you did lines of best fit in algebra 1, so you have done those before. You probably didn't talk about the correlation coefficient then. So if we're looking at our example with our drilling data, would this have been a good line? Is that close to 1? It's not too bad, so it's a pretty decent positive linear relationship. All right. So let's do one by hand. We are going to go ahead and enter this in our calculator just so it can calculate the mean and standard deviation for us, and so we don't have to do all of that by hand. And then if we go to stat, calculate, 2 variable statistics, that way we can just get everything at the same time. So I have x bar is 4, standard deviation x 2.4. let's go ahead and set up a table. So for each of these, we have to do some calculations, and then we're going to multiply those together. So for my one, I have, let's see, 1 minus 4 divided by 2.4495. You can hit second enter, you can bring it up and just change your prices. We'll do the same thing for the y's. So our current y value minus the mean of the y's divided by the standard deviation of the y's. You guys know where I'm getting these numbers? And then we just multiply each row together. You guys all understand what we got this? So now to find R, look back at our formula. R is the sum of those products divided by n minus 1. So now we add all of those up. We get negative 3.7823 divided by n. We had 1, 2, 3, 4, 5 points. So 5 minus 1 is 4. So we get a correlation coefficient of negative 0.9456. What would that tell me about this data?
It's
Yeah, it's a pretty strong negative relationship. Go ahead and do your, let's see what the calculator got for the linear correlation coefficient. So if you go to stat, calculate number 4, they have an R of negative 0.9456. So the exact same thing that we got. Okay, so we can do it by hand or on the calculator. We should be getting the same thing. Question. So the next question is like, how close to 1 is close enough to say that it's a linear relationship? You know, is 0.7 close enough? Is 0.6 close enough? What are the guidelines? So we actually do have some rules on that. We have to find the absolute value of the correlation coefficient. There's a table we're going to use, but it only has the positive R's. Because remember, all the negative tells us is it's a decreasing relationship. So it doesn't really have any bearing. We're just looking on how close it is to R. All right, get out your formula sheet. There is table 2 on your formula sheet. Probably like the second piece of paper, middle of that, the back of that second page. So second piece of paper, the back of it. In the middle it has table 2, critical values for the correlation coefficient. Okay, if R is bigger than this number, then it's linear. Otherwise we're going to say it's not linear. So if we want to see if, let's do this in example 2, the one we were just doing. If I want to see if that was a linear relation. Okay, so in our example 2, we found that R was negative 0.9456, right? What was our sample size? 5. So you go to your table, n equals 5. So that means the critical value is 0.878. So as long as the absolute value of R is bigger than the critical value, we say it's linear. Okay, so is the absolute value of my R bigger than the critical value? So this one is good enough for a linear relationship. Okay.
But where did we get the control value from?
The table 2 that we're looking at on our formula sheet. So back of the second piece of paper. Turn it. Second piece from the front.
Sorry. Oh. I was in the middle of the thing, so it's fine.
So what about the oil example that we had? Okay, we did this from example 1. How many points were there in our drilling oil or drilling rock example? There were 12. What's the critical value for 12? So is the absolute value of R bigger than the critical value? Yes, so that one is a positive linear relationship. So you'll notice the more points you have, the smaller the critical value. Okay. And then Okay, let me ask the question. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of first to unmarried mothers since 1990 is 0.940. Okay, that's a pretty strong positive relationship, right? So does this mean that a higher percentage of females with bachelor's degree causes a higher percentage of first to unmarried mothers? No. We found a very strong positive relationship. Why would you say no then?
They don't have anything to coincide.
We showed that there was a relationship. That doesn't mean that one caused the other. Remember we talked before about lurking variables? There could be something else that has a bearing on both of those things. So you have to be very, very cautious. You can say there's a relationship, but you cannot say one thing causes the other. Another example. Ice cream sales and crime rates have a very high correlation. So does that mean that we should shut down the ice cream shops? Okay, what could cause both of those things to be related? Heat. When it's hot out, do crime rates go up? Yeah. When it's hot out, do people eat more ice cream? Yes. So the ice cream and crime rates had absolutely nothing to do with one another. There was a relationship, but it doesn't mean one thing causes the other. Final example. So because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers want to know whether cola consumption was associated with a lower bone mineral density in women. So this is number of cans they consumed per week and the bone mineral density. The next one, here's the scatter diagram. Correlation, negative 0.806. So what does that tell me? It's a fairly strong negative linear relationship. So the more they drink, the lower the bone density. So we conclude a negative linear relationship exists. Can we say that drinking more soda would cause your bone density to decrease? No. We can say they're related, but we can't say one caused the other. What could be some lurking variables we had?
Previous health issues.
Okay.
Genetics.
What else?
Where you live.
Maybe other dietary choices. So just be very, very cautious. You can say they're related, you can't say one thing causes another. All right, that's all I have for today. So you've got less time to work. It is out of the book this time. You can use the calculator.